So yesterday, actually, we had talked about what fluid mechanics, what was the content, and what need to be studied in various topics of them. So today we will talk about introduction of means only. So in introductions, you have various terminologies and all this. So let's see. So the objective of this particular course, first we should know what the objective of this particular course is. So first objective is understand the basic concept of fluid mechanics. So what fluid mechanics is. So in our course syllabus, we have some of the contents of the fluid mechanics which are the best one for UG curriculum actually. So in sort of that, best for the undergraduate fluid mechanics. Second part is that the recognize various type of fluid flow problems encountered in practice. So fluid flow means how would you transport the fluid, how would you handle them, how would you store them, how would you design their vessels, something, and how would you design the pipeline networking. So these are called various type of the fluid flow problems actually. And how would you control the flow actually? So control means valve. How would you pump them? So you need a pump. And once you need pump, wall, pipes, so you have to design them also, right? So these are various fields from where the problems can be generated, or you can say your ideas would come to do the new one. Third one is once you have identified the previous problems, then you have to identify, you have to model them based on physical understanding or physics of the problem, model them, and then you have to solve them in a systematic manner. Systematic means just like you might have solved in your mathematics, you might have solved simultaneous equations, right? Some would be two variables, some would be three variables, and all this. So each time you have calculated some sort of degree of freedom there. So that time you might have not heard the word degree of freedom, but you might have heard each equations must be consistent, or you should have same number of the equations as the number of variables, right? Only then these can be solved. So you have a systematic approach to solve them, so solve those equations or problems. After that, you should also know the accuracy, that how much accurate you should be in your data or the measurement actually. So accuracy means so accuracy part there means just like a scale. The yesterday we were talking in the lab. So you have the scale marked there. So the minimum thing you can measure there up to 1 millimeter, right? So that is the accuracy of that particular meter. Then you have a pressure gauge, or just like a pressure gauge of your tire of your vehicles. So there you have minimum, I think, 1 pound. So you cannot measure the pressure less than 1 pound there. So if you are somehow you are maintaining 1.5, it means you are doing something from your side. It's not, these are not data given by the your gauge, right? So you should be accurate. What are you mentioning? Sometime uh, then you have precision part also. So precision, significant digits. So here, just like in mathematics, once you do the calculations or any problems, you do the calculations by calculators or by Excel sheet. Generally, you are not bothered that how many digits you are going to put. You will keep on the writing. Some would write up to one decimal place, some would write up to two decimal place, some would write three, some would write four, and some can write up to 14 decimal places. So you have to find what the significant is, what the accuracy of your the or the I mean the instrumentation or your problem needs. Actually, just like you are dealing with money. So money, all transactions do you do in case of dollars, in case of rupees, you are doing a perfect number, just like 1 rupee. Nobody is doing transaction in 25 paisa or 10 paisa, right? So if you are putting that 1 lakh point zero one is of no use. That doesn't make any significance. Fine. So there the factors come significant digits. Then you have dimensional homogeneity of all equations. Let's say you have the equations, you have always a left side and a right side. So your dimensionally need to be consistent. Yeah, let's say you have two terms, one term on the left side, one term on the right side. So dimensions of left side should be equal to the dimensions of the right side. That is called dimensional homogeneity. Second part, let's say you have more than one term in left side, more than one term in the right side. So each individual term dimensions should match. Otherwise, means the equation is not consistent or you have not modeled it properly. So whenever you are modeling or solving something, the first part that need to be checked, are they dimensionally consistent or not? Otherwise, there some people don't pay attention of them. They start directly solving them, and you will not end up with the correct values because you most of the time when you are asked to solve a problem, just like in the engineering course or let's say physics, because so far in first year you have learned physics and some other problem where dimensions are most important. So most of the time you are interested in values. You have taken one values from problem statement and just plug in the equation. You just do the calculations. And you end up with the wrong answer because you are not checking the dimensions. Sometimes the teacher or anyone can give you one dimension in feet, one in kg, one in mks, one in fps, one in cgs. So you have to follow a particular a dimension system, right? So in that case, you should have dimensional homogeneity of all equations that need to be checked first. And each and every term dimension must be mentioned that call a clearly defined equations. Fine. So these are the objective of course actually. Then introduction, what this mechanics is. So mechanics, you can say practically is the oldest science which deal both stationary and moving bodies under the influence of any force. It could be any force. It could be the electrical force. It could be a magnetic force. It could be a physical force. So in case of fluid flow on macroscopic scale, we always deals with the physical force or a gravitational force in case of fluid mechanics. Then you have their branch, their statics there. So statics deals only on the bodies which are at rest. So just like a water or a fluid, if you will fill in some container, that is called the rest only. No motion, the nothing but you are just storing them only. So that is called the statics part. So static case mainly you have pressure distributions actually on the walls. Then you have dynamics. Dynamics means all sort of the transportations. So where you need maybe a closed channel, a pipeline, or the means the any pipe, maybe a plastic pipe, maybe a concrete pipe, maybe a metal pipe, or you should have a open channel, just like your river. So you might have seen the river or canal. So there also the fluid is flowing. So that is called the dynamic part here. Then you have fluid mechanics. So you have added two terms here. Now one is fluid, one is the mechanics. So mechanics on top you have the mention is branch of science which deal with the stationary and moving. Now you have added the fluid. So you just add the fluid everywhere here. So the fluid mechanics, the definition here is this deals with the behavior of fluid at rest. So that is called fluid statics, or in motion, that is called fluid dynamics, and the interaction of fluid with solids and other fluids at the boundaries. So why we have mentioned here other fluids, because you can transfer, you can handle either one fluid or a mixture of two fluids. There those may be homogeneous, those may be the inhomogeneous also. Sometimes you may not have a pure fluid, you will have dust, you have some other coarse particles. So then you have the solid particles in that here. Just like in case of flood, so you have lot of mud in that along with water. So you have solid particles also are there. and their behavior, their nature also will affect your complete transportation part. Then you have fluid dynamics. So you have further segregated your fluid mechanics into this the dynamics part, which deal completely on the motion of the fluid only. So you are not talking about the rest part only, all the motion part, the movement part of the fluid mechanics. So there you have further classification there, a fluid dynamics. Then you have hydrodynamics. So hydrodynamics here you deal the motion of the fluids that can be approximated as incompressible fluids. So incompressible generally we talked about ideal behaviors. So ideal fluid, ideal gas, everything we tell them the incompressible, right? So ideality, this is the major constant that is called ideal part. Incompressible, your density should not practically change. Then you have hydraulics. So hydraulics is being used here just to liquid flows in pipe and open channels. And examples of that, you use the hydraulics just like a hydraulic jack. Have you seen the hydraulic jack so far?
Yes, sir.
Hydraulic jack, wherever you go for car washing, in bottom they have a jack there, and they pump it, and then that your car goes up. So that is the one of the example of hydraulic jack. So all machineries which lift the heavy weights based on the works based on this hydraulics only. And most of the time, the fluid used in this hydraulics are incompressible, because if they will get compressed, your purpose will not be solved, right? Then you have gas dynamics here. So you can say the fluids where you have a significant change in the density, and those are being classified as the gas dynamics. So in gas dynamic doesn't mean that you have only gases. You can have the liquids also in which the density would change by significant amount. So that would be will be taken care in this particular branch of the fluid mechanics being treated as a gas dynamics part here. Then you have aerodynamics here, just like aero, the space where the outside medium is always air, not the water. So just most of the time it's need for aircraft, or the rockets, your automobiles. So rockets here they design its shape and size in such way that it should have less drag on its body. Otherwise, this will need a lot of power, actually engine power, just to move forward. At the same time, the designing of jet also, so that it can get the upward force to move it. Same thing in car case also. So car body also they need to be taken care aerodynamic, how the air will move on wind screen. You see the old car was just like a flat screen, just like a Jeep car, right? In the beginning, their wind screen was this way, horizontal, means completely vertical, and they cannot move faster because they have to face a lot of wind pressure, right? After that, this wind screen has been changed slightly, slightly, slightly. Now you see the race car completely up like that only, right? So that is just to keeping in mind the aerodynamics, because if the air will hit at the 90-degree, you will have more impact force and will be try to drag you backside or push backside. So if you change the direction slightly here, so it will move that side, and on back side it will create a vacuum. Front side you can move with the engine power, so the vacuum and then backside pressure would try to take the place in the vacuum, so it will further push you forward. So it will help in that way. Then you have this meteorology, oceanography, hydrology. So these are just mean the natural flows, meteorology, the weather conditions, the movement of clouds, and oceanography here, the tidals and the geothermal part also here. So these are some classifications of your mechanics. Now we want to define first what fluid is. So can you tell something from your side? You have a lot of things on this slide also, everything. But before I will read or explain it, can you tell what fluid is?
Sir, in the secondary level, we can say any substance which tends to flow is called fluid. But as far as engineering is concerned, we can define fluid as the substance which deforms continuously under the application of shear stress. It's
Right.
called fluid.
Yeah, that is the right definition here. So fluid, what we have here that and any substance which can flow actually that is called here. That's called a fluid actually. General definition and a very crude way you can say any substance which can flow. So in that case you have the liquid also, you have gases also. Now if you say the solid also, so just like see this particular you can see this particular figure here. So what you have a top surface here. Can you see the pointer on this PowerPoint?
Yes, sir.
Yes, sir.
Okay. So you have here top surface, you have here bottom surface. Now let's say in between of that you have some material. Maybe let's say this particular block here, the shaded one is some material. We don't know what is it. Fine. Suppose you are putting a force on top surface here. So what will happen if in case of solid, let's say you have a solid material. So if you have this force quantity is very low, it won't move. Fine. But in case of by chance you will put more and more force, so you can see the solid block also. You have a block. If you have top side force is very high and you have tight clamped it very properly, it will distort the solid, right? So after some force also, it will also make this particular top movement. But this need a high force. So both will the deform on application of shear. Only thing the quantity would change. So that can be there for the solid also and for actually the fluid also. Now once you have this total force parallel to the surface divided by the area of the surface is being treated as a term here shear stress because it works in a tangential direction. So tangential force is being called a shear force, and then the area on which it acts is divided by that particular area will give you the term here shear stress. If it is the perpendicular here in that way, then it's called the normal force, and that area on which it acts perpendicular, that is called actually the that force upon area will give you the pressure force because it will try to compress it. So pressure force either will try to expand it or compress it. Those works always in the normal side, either inside or outside. Tangential force will act in this side, mean the tangential to the surface actually, or you can say parallel to the surface. This will always try to actually try to drag the things. So the definition of the fluid here, you have fluid deform continuously under the influence of shear stress no matter how small the force is. This is the most important point in case of fluid. If you have a force, no matter how low the quantity is, it will deform. But this is not the condition in case of solid. Solid need at least a minimum force to make it flow. So this is the most important point. So in case of solid, the stress is mean the proportional to the strain. And fluid case, you have the strain rate here. So that's what you have. So in the next slide, you can see. So this you can see this what the figure I was talking to you when you will apply the shear. What you have fluid will continuously deform first part. Solid would also deform a band after a certain force only. So let's say the first block here. Here you cannot say what this material is, whether it is solid or fluid, because both are at the rest only. You can't comment and mean anything here. Now you have applied a small force here, so this has moved from here to here. So this movement can be possible in both the materials, in fluid also, solid also, because both can the move up to some extent. Now you have the applied further force is further moved to a new positions. Now here you have some indication because solid cannot move to a larger extent because they will break after that particular point. That's called yield stress, right? So after that particular force, they will break. So you can say here this is some sort of fluid now. Now you have put further force in the fourth figure. It has further the deform again. Now you will put further force, so it will become thinner and thinner and thinner. So finally it will deform continuously. So the difference between solid and fluid is solid would the deform after a certain force. Fluid would deform each and every force, and fluid will continuously keep on deforming. It will never break. So breaking is the point. Continuously deforming means no constraint of breaking. It will not break. You can apply as much force as you can. It will keep on deforming only. Fine. Now here, so you see there the some term here. Actually, that means the stress here. Then you have normal stress, shear stress. So stress is generally force upon area. That's what we calculate it. So here, if you see here, this is the normal. If you have the normal force, so this force acting on this particular surface here divided by this force upon area will give you the normal stress here. So this is treated by pressure or sigma actually, Fn upon dA. Now you have this force component which act in tangential side here, this one. So you can see the tangential side. So tangential force upon the area on which it acts only. So let's say the area on which you have applied. Area means the contact. Here, let's say this one. So if you are forcing here, so area is only on this dot. If your area is just like that, area is completely your palm only. So you have to see that where your point of contact. So that is treated as a area, not the entire surface. Fine. So area here, then you have shear stress here. So shear stress means the tangential force divided by the area on which this force is acting. So that is again same is dA. So this tangential force will try to deform, and this the normal force will either try to compress it or expand it. The two things can be done in case. So you have two terms here, the in the normal stress, shear stress. So pressure is being treated as the normal stress only. Now you have one more condition, zero shear stress. Zero shear means, let's say something you call a rest, just like the Newton's first law of the motion. What does it say? What is Newton's first law of motion? What does it say?
When anything is at rest, it will remain in rest unless and until there will be a force.
Right. It means there is no force, right? Correct or not? And no net force, right? Only then it could maintain its own position. Fine. So same thing in the fluid also. The zero shear is, means the stress means if your fluid is at rest, it means if you add up all shear, all normal or tangential, they must cancel out. So there should not be no net stress in any of the side, neither in the normal side, neither in the tangential side. Only then it can be at rest only. Fine.
Sir,
Now, I guess
sir, isn't there any slip condition?
sleep
The
condition in what?
sir, the relative motion between the surface and the fluid or the substance which we are taking.
Uh, no, because you are talking about the rest, so you are fixing a boundary. Fine. A system boundary, and you are talking about within that the system boundary itself. So
Okay,
relative
sir.
motion part is not coming into the picture here. You are talking about the entire fluid as a macroscopic point of view, the entire fluid as a whole, not the individual particles. So if you are talking about the individual particles, it could be there could be some the relative the motion. Some particle may go this side, some with this side, some with upside. So individual particle may have some motions, right? But what about as a whole? As a whole, the fluid is completely at the rest. It means uh, whatever individual particle, motion, stress, everything is there, that is as a whole is coming as a zero only. So individual particle can have, but as an entire fluid, to make it a condition at the rest, it should not have any shear. Fine.
Okay, sir. Okay, sir.
So that's what you have the definition here. The liquid here, the liquid you have group of molecules that moves on each other here. So, but the liquid case here, just like see the figure here, this one. So the first figure here, you have a free surface, and there this symbol is talk about the atmospheric pressure, or this container is open to atmosphere. So the liquid case, you say that you have a fixed open surface here, and this won't change with respect to time and all this. That is called perfect definition of the liquid here. The liquid molecules are not allowed to leave the surface because their cohesive energy or cohesive force between the liquid molecules is sufficiently enough. It will not try to leave the molecules outside from here. So that is the definition of the liquid. They can move within the liquid, but they are not allowed to leave the liquid surface only because of the cohesive forces. See for gases here. So you see gases here, if you will not close from here, these molecules, some of the molecules may leave the surface. Here the cohesive energies of gas molecules are very, very low as compared to their kinetic energy of the molecules. So finally they can leave actually the surface, and therefore you don't have a perfect free surface in case of gases here. So, liquid will have a perfect surface. So that is the point. So that is the only because of cohesive energies of the molecules. In gases it is extremely low. Liquid it is the extremely high. And solid is too much high actually, so that the molecule itself are not allowed to move beyond a mean free path, right? Yes or no? Hello?
Yes, sir.
Yes,
Sir.
sir.
In case
Yes,
of
sir.
the
Yes, sir.
in case of the
Yes, sir.
solid, in case of the solid, movement is also possible within a mean free path. Okay, liquid they can move in the entire container, but they cannot leave the free surface due to the cohesive energies. Gas cohesive energies is too low, so they are free to move anywhere. If you will leave the container open, some of the molecules may go out. Fine. Then this is called, you have the next example, which I was just talking about the solid only. So this is the solid. All have this one. So they have this is called the mean free path here, this one. But they can move only between here only. They cannot leave the surface. Therefore, their shape and size is fixed. Liquid case, here they can move within the containers, and they have a lot of cohesion energy. So they are free to move, but they are not free to leave the surface. So they have, you can say, fixed mass, not volume. In case of gases here, you see, all are free. Cohesive forces are not there. The molecules are free. So they are free to move, and they can leave any surface actually. So they need a confined boundary. Fine. So these the definition you already know actually. Now here, one thing we want to that define here, let's say you have something is called, one is called gas, one is called vapor. So any substance, once it reaches a critical temperature, is being treated as a gas. Below this critical temperature and in between of boiling point is treated as a vapor only. Boiling point and in case and critical point in between of that, it is just treated as the vapor, just like water boiling at 110 degree or the 100 degree, 120, 130. Those are treated as the vapors only, right? Till it reaches to the critical points. After the critical point, you will treat it as a gas only. Now, the one more term here, this we talk about macroscopic and or we say classical approach. One is called microscopic or statistical approach. Macro means just like you see this container here. So in this container, you see there are the several the molecules which are moving here and there. So there the one person will say, okay, I am only interested what this container is. So don't write anything, I will provide you. Listen to me first. I am not because I will provide you the everything. Don't worry. So macroscopic means just like for this container, one person is just interested. What mean I am not means the interested what is happening in these individual particles. I'm just wondering what is there inside. So let's say you have a container, so you are just interested in let's say how much is mass, how much is total volume, right? How much the pressure at the walls. You are not that means interested how much pressure is being created by this particle or this tiny particles or these two three particles. You are not focusing on individual molecules. So if you are not focusing on the individual the molecules means you are talking about as a whole or the overall change that is being treated as a macroscopic part or classical approach. So this is easy to solve, easy to handle because you will have practically for one container you will have two, three variables, one for density, one for your volume, one for your mass, one for this pressure gauge, right? So you can connect a pressure gauge, you can directly get the pressure inside this entire container. So that is called macroscopic part. Micro means now you are focusing. Let's say I want to say what pressure would be created by this molecule. How much is the heating rate of this molecule to this particular surface. So for each particle, you will have a set of equations. Previously, you have three. Now each particle will have three. So your number of the equation would become extremely large. So those are only uh, can be solved if you highly need them. Just like a trajectory of the pollutant. You have some pollutant from your some coal-fired plant or something, some furnace, you have a pollutant. A lot of pollutants are coming, SO2, CO2, nitrogen, oxygen. There's so many pollutants. Now you are focusing on each pollutant. Where will it fall? Just like a trajectory. So there you need an individual particle, means the approach. Just like in your class, if I talking about my second year chemical engineering, I just need how many the students are there, how many has moved from first year to the second year. So that is called macro part. Micro part now I am further going to the deeper side. How much are mass of each student? How much how many many grades they got A, B, C. So you are just like elaborating more and more and more. You are more focusing on individual particles. So that's called macro. So most of the time in this entire fluid mechanics or a classical fluid mechanics or the undergraduate fluid mechanics, we deal only with the macro part only. Micro part we will not deal. Fine. Then you have applications. Where do we have the applications of fluid mechanics? So you won't find any place where fluid mechanics is not there. Everything you see, just like inhaling, you have fluid mechanics. Breathing, you have fluid mechanics. Pumping of your heart, your valves, everything is everywhere in your entire body is fluid only. Just like your nerve, your vein, sometimes you have contracted, sometimes you have large heartbeats and all this. So you have a lot of applications of the fluid mechanics. And based on that, people are the designing your artificial organs, artificial heart, artificial kidney, liver, lungs, right? So this is only because of that. If you know the better fluid mechanics, only then you can design them, right? Otherwise, you won't be. Correct or not?
Yes,
Yes,
sir,
sir.
correct.
Yeah.
Yes, sir.
So fluid mechanics have a lot of scope actually in all actually. These days, people are doing a lot of designing of human bodies and part because these are previously people used to have some animal, I mean the animal origins parts, sometimes eye of that. But now they are the in the designing everything artificial, some biodegradable something. So you have these are the examples. The natural flows you have from the waterfalls, and then let's say the designing of your power plants. Power plant, you have their very big thermal power plants. Your all your chimneys of your petroleum plants, they don't have pump there to throw out these particular gases. So somehow you have to design this particular column in such a way that all your gases will go up to a particular height so that they will fall after a particular distance. Because if it just come out from the column, just fall something like that, it means you are polluting your plant only, right? So you have to give a sufficient height to the chimney or tower. After that, it should go further height up. Then it will the disperse completely in a over a period of very over the very large cost of area, so that the density of the pollutant can decrease. So there you need the individual pollutant also. So there you need the statistical approach in case of all these pollution control way. Designing of fluid mechanism would help in designing of your tower shape. That how would you give the natural draft so that in bottom side just give a small blower and so that your gasket can go up very with a very high velocity. So this would be you see all this particular tower, they have very huge area in the bottom. On top side you have the narrow one. This is called a natural draft only. Now this boards the designing of your ship or your floating objects. So here you just calculate, you the design is based on your after force, right? The Archimedes principle here only. So you have to design it. You want to have the stability also, so that in case of slight change in bin, it should not topple down also. So you have to see is stability part also. So stability would be calculated in terms of metacentric height, that is your body weight and the center of the gravity and all this. So they should lie in the same line, correct or not? Just to make the stable, right? Then you have designing of your aircraft, mean the spacecraft, your rocket, your fighter plane. So depending on the speed, magnitude, how much you want to give, and that you have to design the shape. Right? Then you have the human body. Entire human body consists of the fluid only. So this have huge scope. Here also designing of car each year, each every 3 months you are getting a new model. Yes or no? What do they do? They don't do any change in engine. Engine is same all the time. They just change the aerodynamics of the car. What they say the very high pickup, right? All the time they say very high pickup, and for that they just change its front. Nobody is doing a lot of work in backside. Backside also matters, but every focus on front side only, because that is the wind pattern that will change your slight change in the orientation will give you a lot of boost in your pickup. So these are the some I mean the examples. Then you have a wind turbines. So wind turbine there that generate the power from the natural wind only. So here the designing of these paddles is most important because they should be in such a way that even if the very low velocity wind, they should generate the sufficient power. But all plants, piping systems, you need a pipe, you need a wall, you need a connection. So you have so many items: a pump, a pipe, a control valve, a fitting. All these total will make the piping system of the plant. And you can see this is the industrial plant here. So industrial plant, everything is flowing. everything is flowing some containers. So everywhere you have the fluid mechanics. Everywhere, each and every segment of your industrial applications have fluid mechanics. So scope of fluid mechanics is very huge. So if you are not good in fluid mechanics part, you cannot design any piping system, any connections actually. So these things we will design, we will do in the next class, the no slip condition part. So today we can end up at this particular point here, industrial applications part.